Hi everyone. When we introduced quantum mechanics, I mentioned the fact that there's something called quantum field theory, which in the context of electromagnetism is called quantum electrodynamics. And it's basically a marriage of Maxwell's equations with the quantum mechanics that was being developed at the time. And so this combination is what we call quantum field theory. And we expect the strong nuclear reaction to be described in the same kind of framework. Now, the framework is easiest for us to approach through something called these Feynman diagrams, where we imagine, in the case of quantum electrodynamics, the electrons exchanging photons of light. Little particles called bosons are exchanged between these fermions. That exchange, in some complicated way, explains Maxwell's equations and the forces of electromagnetism. Well, we want to do something similar with this strong nuclear force. We want to imagine the quarks are actually exchanging some sort of boson between them, mediating this strong nuclear force, causing them to be attracted to one another. We call this new boson a gluon. Really, you're supposed to imagine it's the glue that holds the nucleus together. So essentially, we invent this new particle called the gluon, which exchanges this strong nuclear force. The challenge here is that unlike the electromagnetic interaction, which just has positives and minuses, we somehow have to explain this triplet nature to the strong nuclear force, and that's actually quite challenging. And essentially the way it ends up working is that instead of having plus and minus charges that's associated with this strong nuclear force, we have to imagine a kind of charge that is three-dimensional in nature. And that three-dimensional charge, if you will, that's associated with the strong nuclear force is called color. So we have gluons, we have color. Kind of this silly kind of nomenclature just continues to propagate through this subatomic world. But this notion of color actually has some reasonability to it, because color also is a three-dimensional quantity, at least in computer science. And you know, every monitor has got like three little pixels, a red, a green, and a blue pixel, and those combinations can create the different colors that we see on our screens. And so, you know, fundamentally, color is has got three dimensions to it as well. And so, what happens is that the three colors inside of a proton, well, this is a neutron, 2 d quarks, 1 up quark. So, inside of a neutron, the three particles actually hold the three different types of color. And what happens is that when you stand back and look at the totality is white. And that's the key characteristic to this idea of color, is that the color has got to be able to support a white particle in total. And that's why you have to have three pieces to it. The three pieces each hold a red, a green, and a blue. And then what happens in a picture like this is that a gluon is exchanged between this and actually carries the color with it. And so if these guys interact via a gluon, they will switch colors. And that switch is what actually creates this attractive force, in the same way that electrons exchanging a photon creates an attraction or repulsion, depending on the math there. The same thing happens here. We have an attraction whenever these exchange color. And so you kind of have to imagine this neutron as this kind of this flood of color flipping back and forth, But at any one snapshot, at any one moment in time, there's a distribution like this, but it's constantly going back and forth, mediating this attractiveness that holds that whole nucleus together through this strong nuclear force in the way the quantum field theory works. We can also kind of explain why mesons exist, where you have a pair of quarks only, because as long as the other partner is an anti-particle, it's got anti-color. And so in this case, you can have green, anti-green coming together, and that also is going to create a white particle, a color-neutral particle as well. And so that's why you have these two different ways in which the strong nuclear force works, is that you have a triplet of regular particles, each with a color distribution like this, RGB, or you have a particle-antiparticle pair, which is sharing a color-anticolor pair. And that is what confines the quarks together and creates the particles that make up the nucleus of the atom.